Okay, up to the last question on the exam paper, question 9. So this is quite a complex question. And part A is a show question. So what we've got here is a circle. We're told that it's a unit circle. So it's got a radius of 1. And the tangent to that circle at point P here is shown on the diagram below. And also that tangent here is going through point A, which is 2, 0. All right, so we've got a show question. So show that the equation of the line that passes through A and P is this here. So when we show, we've got to give working out of how we calculated things. So what have we got? We've got a straight line, and so with our straight line, we need the gradient, and we need a point. Now we've got a point, 2, 0, and we need to know the gradient. Okay, so the gradient has to do with the angle. So, because remember that gradient m equals tan alpha. Now, alpha is this angle around here. All right, and so that's what we need, is we need that angle alpha, and once we've got that angle alpha, we'll be able to find the gradient. We've got a point, and then we'll be able to go from there. All right, so we need to find this angle, so we need to give some working out as to how we've found that angle there. And it's a few different approaches, but in terms of the approaches, we've got to find one of these two angles. All right, doesn't actually matter which one, but we've got to find them. All right, so if we take this triangle out, and so from triangle OPM, what do we know about it? Well, we know first of all from what we've been given here. So if there's OP and this is M, we know there's a right angle here. We know it's a unit circle, so OP is a length of 1. Now, point OPM, I don't know why I've got M. Why have I got M there? I don't know where I've dragged that from. It should be OPA. All right. M is our gradient. OPA, and so A is here, and so if that's point A is there, then that distance from here to here is a different distance of 2. So now there's a couple of different, well, actually there's a couple of different, I don't know what I'm rabbiting on here. We could find this angle in here. Let's call it theta, for example. Not for example, we use theta. We've got then the adjacent and the hypotenuse. So that's cos theta equals a half. And so theta then would be pi on 3. All right. So theta is pi on 3, and that's one of our known angles in the unit circle, and known values, exact values. You need to know those if that hasn't become obvious already. All right, and we're after this alpha. Now, there's a couple of different ways that we could approach getting this alpha. We could find the angle down here at A if we like, or we can use exterior angles of the triangle theorem, whichever way you like. Now, the exterior angle of the triangle, if I now let me change my, so if I extend this angle out here and then there's my alpha, which is exterior angle of the triangle. And exterior angle formula says that this angle here, alpha, is the sum of these two over here. So alpha is 90 plus theta, which is pi on 2 plus pi on 3. And so we get then pi on 2 plus pi on 3. Pi on 2, we've got to put it in sixths. So 3 pi on 6 plus 2 pi on 6 equals 5 pi on 6. All right, so you're probably going to need to do that. You're probably going to need to, well, in fact, if you look at the examiner's report, they indicate in that they were looking for how did people get this angle here. All right, let me change back to my blue. All right, so now what have we got? We've got that m equals tan alpha, and from what I defined up here as my alphas, and we've just found that to be tan 5 pi on 6. And again, that is one of our exact values that we need to know, and 5 pi on 6 would be in the second quadrant, so tan is negative in the second quadrant, and 1 on root 3 is what it will be, and I'll just leave it as 1 on root 3 at the moment, and in the end I will rationalise the denominator should I need to. However, hint here, they haven't rationalised their denominators here in what they've asked you to show, so I'm going to leave it there. All right, so then the y minus y1, this is the gradient point form of a straight line. You could use y equals mx plus c if you wanted to, but I've just done that. So what have we got? We've got the gradient we've just found here, a point. So I've got this point here. Point A is what I'm going to use. So point A which is 2, 0. You then get y minus 0 equals m, which is negative 1 on root 3, bracket x minus 2. And so y then equals, and multiplying this in so that it looks like what you've been asked to show, it's negative x on root 3, and negative and then times the negatives are positive, 2 on root 3. There we go, shown what we've been asked to show. Okay, so if you look on my website, on my scan solutions, I've done it a slightly different way to that, but it doesn't matter. Both give you the same answer. Also, if you look at the examiner's report, you'll see they found the coordinates of point P and use that rather than A. Well, that's not necessary. You can use point A. You can use any point that's on that line. All right, so there's part A. Part B, now we've got to be careful here with some wording so we don't get confused. So we've got a transition matrix. So let's have a look. So 1, 0, 0, Q. Q is anything except 0. Let the graph of the function h be the transformation of the line that passes through the points A and P under T. All right, so that's this straight line here. We're going to do a transformation of it. Now, when you look at this matrix here, you're multiplying by the x by 1, so you're not changing the x at all. And 0 times y, 0 times x, then q times y. So 2q times y, so we're looking here at a dilation in the y direction. So this line's being dilated in the y direction. So what does that mean? Well, this point here is on the x-axis, so it's fixed, but this point here is going to move up or it's going to move down. All right. So if that's now asking, find the values of q for which the graph of h intersects with the unit circle at least once. So now, as I said, remember I said this point's going to move up or down. So let me see if I can do some things with a line. So here's our line going through here. And so there's the one we found, right? And now that can move up or it can move down. Now it's talking about, it says, we want to know the value of q for h intersects at least once. So this is h, this red line I'm moving around. It doesn't intersect the circle at all. Here it intersects once. Now it intersects twice, all the way down here, all twice, 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 still twice until we get to there. All right. So what are we interested in? I'm going to draw a little unit circle here. So I'm going to draw that circle. Now, they don't ask you to draw these circles, but they might be useful. So here's our point A, which stays where it is, and there's our line. Now, at the moment, it intersects once there, and as you saw when I swung that around, it comes down to intersect there. Now, this gradient of this line here, we figured that out. We figured out that up here, and that gradient is negative 1 on root 3. All right, point A, of course, is 2, 0. And so this gradient, that one there, now that's really essentially just a reflection. So it's a reflection of that line down onto there. So if that's a reflection in the x-axis, it's going to have a gradient of negative 1 on root 3. All right. So what are we interested in for q? Well, we don't want, so here's our original that we've got, 1 on root 3. We don't want it to be that point to move up. So we don't want q to be bigger than that. But q can be something that lines us up with 1 on root 3, which would be 1. If q was 1 times y, then that point stays where it is. All right. So q is an element of, all right, so there's 1 at that end if it's 1. Now to get this one over here, the reflected one, it can be negative 1 to get the reflected point. And they're okay, they're included because they're where it says at least once, so they're where it intersects once, so they're included. Now I've put it in 2 parts. I've done it like this because here, look here, it says q can be anything, but it can't be 0. So between negative 1 and 1, what we can't have is we can't have 0. So what we need to do is we need to say, okay, we can have anything from negative 1 to 0, so that would give a line down here, but not 0. And then we can have anything that's in here, but not 0. So I need to write that in this form here so that I can exclude the 0, because the 0 for q is not included because of the information we were given. All right, so you probably need to think about that one for a fair bit, because that can be a bit tricky, that question. Now it says here, let the graph of H intersect the circle twice. All right, so no, I haven't got, so that's when my line goes through here somewhere. Find the values of Q, I should say, for which the coordinates of the points of intersection have only positive values. So the coordinates of the points of intersection have only positive values. All right, go think about what does that mean, only positive values. Only positive values, well, let's go to that circle again. Only positive values are the points of intersection. It intersects twice. So here's our one where it intersects the once. And here's something that intersects twice. Now it says coordinates of the points of intersection have only positive values. So when I look, this has got 2 points. Positive x, positive y. Over here, so negative x. Negative x. Now if I go down here, again we've got negative y value, negative x, and negative y. So my y coordinate, excuse me, my y coordinate that I'm looking for, where are we? Find values of Q for the coordinates of the point intersection have only positive values. All right, so I could, and we're talking about intersecting twice, so let me change my color so that I can draw it. So we're talking about intersecting twice. The values of Q for the coordinates of the points have only positive values. All right, so anything from there all the way through to not including something that goes there. So the values of Q that fit that range. All right, so between, but we're talking about intersecting twice, so it's a bit more complicated. And the points of intersection. So this line I've drawn there is actually no good. So let me erase all of that and explain to you why that is no good. Because we're talking about 2 points of intersection, and we're after 2 points of intersection which have all right, so we're looking at 2 points of intersection. All right, these diagrams. So here's the one that we've got with our P and our A. So there's our P. So 2 points of intersection. So if I've got one in here, both of those points of intersection have got positive values. When I get to here where this one's going through there, that's now got, that point there is now 0 and 1 for this point. Once I go past that down here, this point over there has now got a negative, and I mentioned that before. So we're actually only interested in lines in between those. All right, so we're looking for a y coordinate being between 1, so we're looking for the y coordinate being an element of 1. Now we don't want to include 1 because the x coordinate, the x coordinate there is 0, and 0 is not a positive number. And this line I've got with my tangent, well, it's only got 1 coordinate, not twice. And from up here in part A, y equals mx plus c, there's our C, which is our y-intercept, so between and 2 on root 3. All right, so that's for our y-coordinate. So how does, what we're looking for is the q values, though, all right? So q values. So to get this 1 here, what we've got to do is we've got to multiply our y-intercept, that's this one here, from our original line. Remember that tangent, that's this line here. So we've got to multiply this y-intercept by something to bring it to there, which is q. So we've got to times q by q, 2 on 3, 2 on root 3, I should say. So in this case, q would be root 3 on 2. And the other end here, when we want to get 2 root 3 as our 2 on root 3. So our q then is got to, of course, it's simply got to be 1. So q then is, and we've got to put this in the right order. All right. So our y-coordinate was 1 to 2 on root 3. So that is root 3 on 2 that corresponds with the 1, and the 1 here which corresponds to the 2 on root 3. All right, again, there's a whole bunch of stuff in that, and it can be difficult to figure out what they're actually talking about. So if you need to go back and read over that and listen to that again, by all means do that. All right, quite tricky getting your head around that. All right, these little diagrams that I've drawn here, all right, they don't ask for that, and this up here, they don't specifically ask for that, but it's going to make your life easier when you've got those kind of things to refer to. All right, so we now move, and also, while I think about it, be careful, don't write stuff outside that box. This stuff out here might not scan. All right, so for C, so before q between 0 and 1, okay, so q being between 0 and 1, point of intersection of the graph where p dashed is always the point of intersection that's closest to A. So what we'll look closest to A, so see this line intersects twice. What we're interested in is this one. So we're only interested in any points of intersection in the first quadrant. All right. All right, so let G be the function that gives the area of the triangle OAP dashed in terms of theta. All right. So what do we got? All right, so theta, let's have a look. So when we refer back to this first part, and that's why I put my angle down in here, because it's made my life easier. However, mind you, I didn't know that until I'd actually done the question. So if you read my scan ones on my website, you'll see that I've worked out this angle. All right, anyway, I'm waffling. So we worked out this angle. So for P, when there's one point of intersection in the first quadrant, because remember, if we go any further higher than that, we get none. So this is our limiting, and that's pi on 3. All right, so we know already from part A, we already know that theta, the biggest that theta can be, this angle here, the biggest it can be is pi on 3. All right, now here it just says point of intersection is closest to A. So it's P dash is a point of intersection with the circle. All right, so it doesn't say how many times it's got to intersect. It just says it has to intersect, and we're interested in the one that's closest to A, if there's more than one. All right, so that's our biggest value we can have. The question is, what's the smallest? All right, and so it's Q between 0 and 1. So if Q is between 0, so that's the theoretical one across here. All right, so that's when this point P dash is actually moved right down to there. So this theta, the smallest it could be, would be 0, and because that 0 corresponds to Q of being 0, which it's got to be bigger than, we need to have that curved circle there. Curved bracket, not curved circle. All right, so what do we know then? Area. So G being the function that gives the area. So we're looking at area. All right. So the area you can get from a half base times height. The half is a half. The length of the base here is all the way out to there, 2. And the height. So the height would be that length there. Now that length there, we know that's 1. And we know this is theta here in this corner. And that's sine. So to get that height, we would just do 1 sine theta. All right, and so 2 times a half is 1 there, and so we've got sine theta. All right, now we need to be careful here. It asks us to define the function g. I've just written area, so I need to define the function g. And so I need to write it as g of what? Now, here, look at my function here. My function here is theta, and it also here says in terms of theta. So g of theta, so if you wrote g of x, you wouldn't get all the marks, is sine theta. And of course, there is some restriction on what theta can be, and which I've talked about up here. And theta is an element of 0 to pi on 3. All right. So fair bit of geometry in this question. All right. So determine the maximum possible area of the triangle. All right. So now let's think about what we're doing here and what the area of this triangle. So the base length doesn't change. This angle gets smaller, and as that angle gets closer to 0, we know that sine gets closer to 0. So our maximum area will be when theta is the maximum. All right, and theta is a maximum when theta is pi on 3, because that's the biggest it can be. All right, so determine the maximum possible area. So the maximum area is equal to g of pi on 3, which is sine of pi on 3, which is root 3 on 2 square units. Right, so there's 2 marks here, so there's got to be some sort of explanation as to what you've done here. So what I've written is kind of what I would say. I would say maximum area when theta is maximum, and the maximum area there's g of pi on 3 sine of pi on 3, and there's your final answer. All right, so there's the end of question 9. So it's fairly complex, fairly complicated. So you need to be careful. I'm just looking at some of my notes at what I've written about this. So be careful, could be confusing. I already mentioned that. All right. Yep, and fair bit of geometry. I already mentioned that to be useful. All right, so that's it for question 9, and that's it for the paper.